Hey guys, I am Gautam from IIT Kharagpur and welcome to GKMX. In this video, I am going to talk about the NMR, how the NMR peaks originates. Okay, so from the different molecules, different organic compounds, how you will get the NMR peaks and the basic theory behind the NMR peaks. Okay, so to discuss this, so first let's discuss about spin coupling. So you have to understand first the spin coupling. Spin coupling. So what is spin coupling? Spin coupling means, suppose let's take a system like that. So a system which here one hydrogen, here another hydrogen. So here we mark this as represent this HA and this HB. So HA and HB. So how HA and HB gives the NMR peaks with particular splitting or particular splitting pattern. Okay, this will be the important. So you know that we have already learned that systems like, suppose this is the hydrogen, so this will have one spin that is represented by plus up or minus up, that is alpha, that is beta, alpha spin or beta spin. You have already learned in my previous video. So if you did not check, then click the I button and you will get the this is part 4, so you will get 3 different videos on NMR. Okay, so this, suppose this is H alpha or H beta, or H which is spin plus up or minus up. Okay, so now this hydrogen and this hydrogen couples, and after coupling they will give the NMR peaks. Okay, this is the basic theory. So how they will couple, how they will give the NMR peaks. So to know this, just keep watching. So here let's consider HA and HB are chemically and magnetically non-equivalent, because if they are equivalent, so they will give only one system, one peak. Okay, because they are equivalent, but there I am considering this, that HA and HB are not equivalent, chemically and magnetically both. Okay, so say this shows plus up spin state, this shows minus up spin state, suppose. Okay, or you may think that this one shows plus up and another shows plus up. Okay, I'm just considering that this shows plus up and this has minus up. Or you may consider only this shows plus up. Okay, so if we apply the magnetic fields, then what will happen? So this HA will couple with HB. How? The coupling process is quite different. You may think that HA, the adjacent HB, so it may couple. So the 2 important points, that is, first point is, suppose if one proton, one hydrogen atom need to couple with another one, then it should be the another hydrogen should be present adjacent of the previous hydrogen. Okay, because here this carbon, here this carbon. So suppose here is another carbon and another hydrogen is present, so this hydrogen will not couple, never couple with this hydrogen. Okay, but this one will couple because with this hydrogen, because it is adjacent. Okay, so I'm not considering this one, and for that I'm just considering HA. So HA will couple with HB by 2 ways. Okay, in 2 ways. So the first way is this should be adjacent, and the coupling process will be like this. HA first will couple with carbon electrons. The nuclei, of course, carbon have nuclei, but here the coupling process should be with electrons, you may say. So HA will couple carbon, then this carbon will couple with this carbon, and finally this carbon will couple with HB. So these interactions, this kind of interactions, that is from here to here, then here to here, then here to here, this kind of interaction will actually happen. Okay, so this is the coupling process, and what we get during coupling. So HA when HB, when HA and HB couples, so first, suppose this has spin plus up, it may resonate, or the HB will resonate with same coupling, same spin. So HA HB. So if HA has plus up spin state, it may align with HB also may align with HA. Then it will have plus up spin state. But if HA has plus up spin state, but if HB doesn't align with the HA or HA's spin, then it will be minus up. So thus we can say that one proton couples with another proton in two ways. First, it will align, or second, it will not align. Okay, so thus it will resonate, the second proton will resonate due to first proton two times. Okay, so because of this, the first proton, that is HA, will show, or you may say will show the two peaks. Because of the first one peak, there is for aligning, and not for aligning the second peak. Okay, so this one peak, second peak, so HA will show the two peaks. Similar same case is true for HB. HB will couple with HA with it may align, or HB will couple with HA when it is not aligning. Okay, so it will also give two different peaks. Okay, say this is HA, this is HB. So in this way, two protons coupled with each other and gives the NMR peak. So here you can see that the HA couples with HB, only one proton couples only with one proton and give two peaks. Suppose there is another proton over here. Suppose this is also considering HB. Okay, so then 1, 2, so it will couple with this, it will couple with this, and don't think that this will couple, this HA will couple two times with this, not like that. Two protons, okay, so with two protons it will couple three times. Only the number of adjacent proton, that is n, say n, then you have to add 1, so it will couple once more, because in the first case, so HA will couple with HB, okay, and this HB, okay, so this will give two coupling state. Okay, say this is plus or minus or whatever, anything can happen, and then two HBs may not align with HA. Okay, so then it will give another coupling state, that is minus up. So these two coupling state will give total three coupling pattern, or three splitting pattern peak, NMR peak. Okay, so you just have to consider the n+1 rule, or n+1 formula. So considering n+1 rule, you will get the three different peak for if two adjacent protons are present, and two peak if one adjacent proton is present. So the condition you just got, that condition is HA will couple with only adjacent protons, nothing else. Okay, and also same is true for HB. Okay, so and also this will couple with this or this if HA and HB are magnetically and chemically in non-equivalent. If they are equivalent, then both are equivalent, so they will not couple to each other. Okay, so this should be chemically non-equivalent to each other. Okay, so now coming to some example, and I want to give you some examples so that it may help you to understand. So say there are different number of adjacent protons and number of peaks. Okay, so the number of adjacent protons, that is, it may be 0, that is there is no adjacent proton. This is 1, 2, 3, 4, 5, and so on. So what we get, you know the formula that I have already said, n+1 rule. Okay, so n is the number of adjacent proton. So here number of adjacent proton 0, that means like this system, suppose H and C with this carbon, another 3 carbon are present, so here also carbon. So here is also same, there is no adjacent proton, so with this hydrogen there is no available adjacent protons to couple. Okay, so that is why the number of adjacent hydrogen will be, the number of adjacent proton will be 0. Okay, so for this case, only this hydrogen, that is the one hydrogen, will couple with itself, you may say, or it will not couple. So the peak you will get only 1, okay, because of itself. Okay, so only number of peak 1, and it satisfies the formula n+1. Okay, so for 1 plus 1, that is 2, for 2 plus 1, that is 3, this is 4, this is 5, this is 6, and so on. Okay, so for 1 it will we can say that peak is singlet, for 2 this is doublet, for 3 this is triplet, for 4 this is quadret, for 5 this is of course pentate, for 6 this is sextet, okay, for 7 this is so on, septet, and so on. Okay, so you will get everything about this fix. So singlet, doublet, triplet, you should know all this, because in the NMR peak you will not you will never see that here is written singlet, doublet, triplet. They will just write S, D, T, Q, P. Okay, so you have to understand, you have to remember all this one. Okay, so let's give some example and let's see what kind of peak we will get from those kind of organic compounds. Okay, so the first example we will take, or I am going to take, that is like this. This is beer, this is also beer. Okay, so just one, this is two protons are present, so we are considering this as proton A and this is proton B. Okay, so you already you know the n+1 rule that says the number of n is the number of adjacent atoms, adjacent protons. So for A will give what will be the number of peaks? A will give the number of peaks equals to n+1. Okay, so n is the number of adjacent proton of A. Then A has number of adjacent proton. This is carbon, nothing else. Okay, so this is the carbon and only one hydrogen atom. So number of adjacent proton is 1. So A will give, n is 1. There is 1 plus 1, that is 2. Total 2 peaks. Similarly, HB will give, it will couple with HA 2 times. One is aligning with one, will not be aligned. Okay, so HB also will give 2 peaks. So for HA that will give 2 peaks. For HB that will give 2 peaks. So the peak will be like this. So you know here the external applied magnetic field. Okay, so increases like this, and this is the reference generally used, TMSCL. Okay, and it is in the 0. Okay, it marks as 0 the reference value. So here 1 2 3 4 5 6 whatever. So then this connected with chlorine, or nearly with this proton the neighbor electronegative atoms are chlorine, and with this the attached electronegative atoms are bromine. So you know the electronegativity of chlorine is greater than bromine, so chlorine will attract the electron towards itself much more than the bromine. So the electron density near this hydrogen, this proton, will be less in case of HA, and in case of HB slightly greater than HA. Okay, so that is why the number of electrons or the electron cloud near the HA will decrease. That causes the HA that will give the HA at lower externally applied magnetic field, because that means if we apply the external magnetic field at lower strength, then it will easily resonate and will give the NMR peak. Okay, as I have told you already in my previous videos. Okay, so you can check my previous videos, okay, by clicking the I button. So whatever, so HA that is attached with more electronegative atom, and HB less electronegative compared to Cl. Okay, so this will resonate fast, so that means it will give lower field or lower externally applied magnetic field region, that means like this way, or this will give towards slightly this way. Okay, because the electronegativity difference is not that much. So this will give 2 peak. So I will consider the height, okay, little bit later. Okay, so I'm just giving here the height, here also 2 peak. Okay, so this will be A for HA, this will be for HB. Don't forget to mark with HA or HB, because it should not be HB or it should not be HA. Okay, so you should mark all these by HA or HB, what kind of protons they are. Okay, so whatever, 2 peak, and their height, you can see that these 2 height is same, this for these 2 height also same. So what height actually means? Height means actually the intensity of this NMR peak. Okay, so this measures the intensity. So how intensity or how you can draw the intensity, or you can see the intensity in a simple system. So theoretically intensity, you can remember this like this way, that is, you can consider one table that will help you to remember all this. Okay, and you can remember the formula, but I will suggest you to remember the table. Okay, and that will be like this. So it should be very helpful if you remember, you can remember this table. So here 1, then 1 1, then another 1, here 2, here 1, then 1, then 3, then 3, then 1, then also 1, then 4, then 6, then 4, then 1, so and so on. So it's tough to remember this table, so that's why you can remember one formula, that is, you know, from your school days, that is 1 plus x to the 4 n. What does that mean? So if you put here, the n is the number of adjacent proton. So if you put here, so consider this one, n is the number of adjacent protons. So if you put 0 over here, then you will get 1 plus x to the power 0, that will give 1. So this is 1. Okay, singlet for this, put here 1, so here it will give 1 plus x. So you just need to take the coefficient, only the coefficient. Here 1 is 1, so you just you don't need any coefficient, but here 1, so that is 1:1. So if you put 2 adjacent proton, that is 1 plus x whole square, then what we get? 1 plus x square, sorry, just write the formula like that way, 1 plus 2x plus x square. Okay, so x square means here 1, here 2, here 1, 1 2 1 1 2 1. Similarly, if you put 3, then you will get 1 3 3 1. Okay, you know, and just put the formula in the right way, not a square plus b square plus 2ab. Just put here like a square plus 2ab plus b square, as we have learned all this. Okay, so this is only the shortcut or the method of how to remember this formula. Otherwise, you can remember this one. So this will help you to determine what should be the actual peak height. Okay, so just if we let's take another example so that you can apply this formula, simple formula, and that will give the full explanation of this one, what I have told you. Okay, so let's take another example, like I should take another hard example like this. So it's not hard, but a little bit complicated than the previous one. I am marking H and HB because all the H's are equivalent, chemically equivalent, all the HB's are chemically equivalent. Okay, so sorry, so H, there are two H's. So there are two H's over here. Okay, so H, these two are chemically equivalent, so these two will show only one, as you can think only these two are actually only one proton. Okay, so this chemical equivalent, so this I'm considering only this, say, as they are chemical equivalent, so this will give 1 2 3. This has 3 adjacent protons, so 3, that is applying n plus 1 rule, you will get 3 plus 1, that is total 4 peaks. Okay, so 4 peaks, that means HA will give 4 peaks. So here HA, and here as the electronegative atom attached, so you can easily consider that the electron density will decrease, so that is why it will show the peak at the lower field region. So there will be 4 peaks, so 4 peaks means 1 2 3 4. So this will be the number of, this will be the intensity order. So 1, then ratio will be 1:3:3:1, that means height 1, then the height will be thrice of this one, and similar for thrice, and then 1. So height will be like this, 1 thrice, again thrice, again 1. Okay, and the for second one is 3 HBs are chemically equivalent. Okay, so these 3 of course we can consider as only 1. So this will give, there are 2 adjacent protons, so that will give 2 plus 1, that is total 3 peaks. 3 peaks, that means this one 1 2 1. So 1:2, that is the twice height, then 1. So 1 twice height 1. That means the height of this will be higher and the height of this will be lower. This is the theoretical model. Actually, in the experimental model, just you can see the slight difference. Okay, this will be slightly higher, this will be slightly lower, but theoretically you can explain in a right way if you remember this formula or this table. Okay, so this is the shortcut. Actually you can easily determine the NMR peaks of a particular simple system. Okay, so now I want to go to further deep and make you understand, make your concept clear totally. Okay, so let's take an example like this. So this is Cl, this is carbon, this is chlorine, this is hydrogen, and also this is carbon, this is chlorine, this is hydrogen, and also another system. This is hydrogen, this is hydrogen, this is hydrogen. Okay, so suppose this is HA, marking as HA, this is represented as HB, represented by AC, AC, AC. Why AC? Because these three are chemically equivalent. So here you can see that there are three different type of protons. All are chemically non-equivalent. So first let's consider HA. So how many peaks it will give? Okay, so HA will couple with HB. So number of adjacent proton is only one. This is not as these are not the adjacent protons, so we should not consider AC. Okay, so just consider HB, and the number of adjacent protons are 1. So that will give, if we consider n+1 rule, that will give total n is 1, that is 1 plus 1, that is total 2. So HA will give total 2 peaks. Okay, you know that all this, but there is a trick over here. So let's consider now AC. So this is HA, let's consider AC. AC 3, all three are equivalent, so just consider 1. So AC will give 1 adjacent proton, that is 1 plus 1, here also 2. So AC also give 2 peaks, and finally it will give 2 peaks, and finally we are here to calculate the number of peaks given by HB. So you can see that in case of HB, in that side there are protons, only one proton of course. In that side, in this side, 3 different kind of protons. So both the side you will get different kind of protons. Both are chemically non-equivalent, but the number of protons present in the both the side. So what you should apply? Should you apply the n+1 rule over here? So actually the answer is no. Here it's you need some kind of modifications. Okay, that's why I am giving you some kind of example. In the previous examples, we have seen that only 2 carbon systems are present, and in it just couples with the adjacent, or it just couples with these adjacent protons. So if you get those kind of systems, then it's okay. But if you get this kind of systems, then you should do some modifications in your formula, that is in your n+1 rule. And the modification is like this. So I am considering Na plus 1, Nb plus 1, Nc plus 1. This is general formula, not HA, HB, AC. They don't compare with this. This is the general formula that I have written over here. So this is the formula. So it can be extended by Nd plus 1 or Ne plus 1 and so on. So what is important here? So what is Na? So Na is the, suppose we are considering HB. This rule will not be applied for AC or HA, because for this only one side we will find protons in the only one side of this system. Okay, so it will just couple with HB, or AC will couple just couple with HB. But in case of HB will couple with both HA and AC. So you can think the coupling process like this: HB first couple with HA, and then it will give 2 protons or 2 peaks. Then each peaks will couple with AC. It's quite different, but let's apply this formula, and then you will find easily the number of peaks. Okay, so first here HB, that will give, so for HB 1, that is Na, say consider this is Na, 1 adjacent proton towards in this is this direction, and 3 different protons towards this direction. Okay, so we just need Na plus 1 and Nb plus 1. So we just need here only this part, not this part. Okay, we don't need. So we just need the first 2 parentheses. So that will give Na, that is number of hydrogens 1 plus 1. Okay, and here Nb, the number of hydrogen 3, that is 3 plus 1. Okay, so 1 plus 1, that is here 1. Na, Nb is 3, the 3 hydrogen proton of Hb, that will give 2 cross 4, that is 8. So we will get total 8 structure in case of H peaks for Hb. So we will get total H peaks. So this is all about this kind of systems, and now I just want to consider some aromatic systems. Like let the first aromatic system like this X. So say X is halogen, that is chlorine, bromine, iodine, etc. So this will give actually complex multiplet. That means a lot of peaks you will find. There will not be any particular number of peaks. Okay, so that is why it is complex multiplet. Why? Because these two protons adjacent to these two protons are far away from these protons are more far away from the halogen atom. Okay, so that is why each proton will couple with each other, and each protons are different because these two are different from these two, and these two you can say chemically equivalent, but of course it can be chemically equivalent, but this is not chemically equivalent, or these two are not chemically equivalent. Okay, so that is why each will couple with another one, and that will give the complicated structure and complex spectra or number of peaks you cannot find from here. So that is why it will give the complex multiplet. So these kind of questions you may face in JAM examination, because in the previous years, maybe 2017, you should if you check, then you will find this kind of questions. They ask some questions like to find out the number of peaks in aromatic systems. So if in case of X, in the place of X there are R groups, that is of course the alkyl groups, then you will find only one singlet, not complex multiplet, because here in this case the number of peaks will be 1. Why? Because R is not that much effective group, you can say, that makes the 5 protons different. And also, if as it is R group, so there are hydrogens in this R group, so the proton on this R group, in this R group, and the protons over here, okay, all protons, the electronegativity of all these carbons, this carbon, and also in these carbons there, because it's a alkyl group, so the electronegativity difference is very less, or you may say the electronegativity difference is very low. Okay, that is why the corresponding hydrogens are nearly identical or equivalent. Okay, so that is why it will just give one singlet. Okay, so for X complex multiplet, for R singlet. So another thing is that suppose you are considering structure like this. Okay, first let me clear some parts of the board. Okay, so say systems like that. So this is H, this is H, this is H, and finally here methyl, here methyl. So here also you will find, you can imagine that here you can find the complex multiplet. Why? Because the 4 aromatic protons in this is orthoxylene, so the 4 aromatic protons of orthoxylene appear as complex multiplet because here say this is Hb, and this is AC, this is AC. So here 2 Hb, this one and this one, these 2 Hb protons are chemically and magnetically equivalent. Okay, these AC protons are chemically and magnetically equivalent. Okay, but Hb protons and Hc protons are, Hb and Hc are not chemically and magnetically equivalent, or you can say non-equivalent. Okay, therefore all protons, okay, all protons couple with each other because chemically as non-equivalent. This complex system, this one couple with this one couple with this, and finally we will get a complex multiplet. Okay, so multiplet means you will get more than 6 or 7 peaks. Okay, so beyond that 4, 7, 8 peaks, we'll say that we are getting multiplet. Okay, so for 2, 3 peaks we can say doublet, triplet, quadruplet, but more than that we will say that we will get complex multiplet. Okay, so this is all about the systems like this. And then coming to last system, that is about the systems like that. This is aromatic ring. Here it is NH2 group, here it is Cl, here it is Ha, here it is Hb, similarly it is Ha, similarly it is Hb. Okay, I'm first I have considered these two as Ha and these two as Hb. So what we get? So first I am giving you the answers. Doublet. So why it is double doublet? Because Ha chemical equivalent, Hb chemical equivalent. Okay, so you have I have already given this example in my previous videos, so you can check my previous videos. So whatever HHB, HB, both are chemical equivalent, but H and Hb are not chemical equivalent. So Ha will couple with Hb, as there is no H atom further. So Ha will couple only Hb, and Hb will couple with only Ha. So this will give one peak, two peak for Ha, and one peak, two peak for Hb, because for this one hydrogen atom, for this one hydrogen atom. So you can easily apply the n+1 rule. Okay, and you will get the number of peaks. So one peak, one double peak, another double peak. So double doublet, the number of doublet 1, 2, double doublet. Okay, so hope you can understand all this. And for if you have any query, then you can ask your query on my Facebook group. So you can join that group. You will get the link in the description below. Okay, so just check, join there, and you can ask your queries, and your friend, YouTube friend or me can help you. So you can help each other also. So that will help you much more if you answer your friends questions. So whatever. Thanks for watching.